For only 10 minutes. So today I will be your host. I am Nasriza and I will be the popular host today. Guys, did you know today is the Maxwell's birthday? Sure. So today we will discuss with you about Maxwell equations. So before we discuss with you deeply with the special guest, we will share with you a documentary. So let's watch out.
Back with me, Mizan, in NTV Zero News. Today headline is about James Clerk Maxwell, or best known as Maxwell of his theory. He is born in 13 June 1831 in Scotland and died on 5th November 1879 in Cambridge. He is a successful Scottish physicist for his formulation of electromagnetic theory. The concept of electromagnetic theory originated with Maxwell and his field equation based on Michael Faraday's observation of the electric and magnetic line force. In 1931, on the centennial anniversary of Maxwell's birth, Einstein described Maxwell's work as the most profound and the most fruitful that physics has experienced since the time of Newton. Without Maxwell's work, radio and television could not be worked. That's all from me. Thank you for watching.
Oh, did you enjoy the documentary just now? Have you learned something? This must be nice. So let's discuss the Maxwell equation deeply with our two special guests today. So in our studio we have the doctor. They are from Maxwell Students Organization. Thank you for coming today. So on my right, she is Dr. Ivy Fakri. She is from Osaka University, and next to her, Dr. Wayan Singh. She is from Tokyo University. So are you ready?
Yeah, sure.
So let's start. So first of all, Dr. Wayan Singh. Before this, I have read about this Maxwell equation.
Yeah.
They are describing about the del V, del and so that. I can really understand about that. Can you explain with us about this Maxwell equations?
So, sure. So I'll start my explanation for the two first Maxwell equations from the set of Maxwell equations. So when James Maxwell first created his dream team for the electromagnetic equations, he started with the ideal of the previous physicists that had discovered about this one, and he tend to put it together into the set of Maxwell equation, which is the Maxwell equation we are introduced now, which is the four equations, and for a better understanding. So the first Maxwell equation states that the total electric flux passed through any closed surface is proportional to the charge enclosed by the surface. So the case we are trying to mention here is any shape that totally completely encloses the charge, like sphere or any three-dimensional shape. The electric flux is the measurement of electric field through any given area. So mathematically, what we get here is the integral of the electric field over the area is equals to the charge over permittivity of free space. As we know that the electric flux density is equals to the epsilon naught E, so the equations will turn out to be the integral of ds equals to Q enclosed, which is the charge enclosed by the surface. When we apply the divergence theorem, we will get that the integral of ds will equals to the integral of del dot d dv. As we know that the Q enclosed is also equals to the volume charge density, which is rho v dV. When we compare back with the dV, del dot dV, we will get that del dot v dV is equals to rho v, which is our first Maxwell equations. So now I'll explain about the second Maxwell equations. So the second Maxwell equation is also a form of Gauss law, but only with the form of magnetic flux instead of electric flux. As we know that the magnetic field being created by the dipolar, which is North Pole and South Pole, the magnetic field line will always go out from the North Pole and entering back to the South Pole. By the reference of a Gaussian surface around the magnet, which I will show in the animation later, and we can see that the total magnetic field line that entering out from the surface is equals to the total magnetic field line entering back to the surface. This gives the overall magnetic field lines will be equals to 0. From this animation, we can see that we can conclude it with the equations, which is the integral of v dot ds will equals to 0. So the same thing goes again with the divergence theorem. We will get the integral of del dot v will equal to 0. From the comparison here, we can see that we can conclude this with the second Maxwell equation, which is the del dot v will equals to 0. That's what all about the first and the second Maxwell equations. Right?
Thank you for Dr. Wayansing for your explanations. I have a little bit about the ideas about these Maxwell equations. So guys, have you any ideas about these Maxwell equations? I hope so. So before we continue with our discussions, let's have a Kit Kat and take a deep breath. Let's rest.
Welcome back to PFD, which is Physics for Dummies. Again, we are here with Dr. Ivy and Dr. Wong, and I'm your co-host, which is Adila. So before this, Dr. Wong already discussed about the first two Maxwell equation. So we will continue our discussion with Dr. Ivy about our next Maxwell equation.
Thank you, Adila.
Alright, let's move on to the third equation of Maxwell's. For the third equation, it is called as Faraday's law. This, we have to consider that a coil of a wire, we will push in and out of the coil. Consequently, when we have a moving bar magnet in and out of the coil, a current will flow. The direction of the current will keep changing. If it will go to one direction, it will push into the coil, but come out to another direction if the bar magnet is pulled. But the current will produce if and only if the bar magnet is moving. So there is no current when you simply hold the bar magnet steadily in the coil. This is what we call an induced current. The induced current occurs due to the change of magnetic field. Now, if there is a current flowing in a coil, there must be a change in potential difference, and that potential difference is an electric motive force, which is EMF. So according to the law, Faraday figured out that a changing magnetic flux within a closed path an induced EMF or voltage within the circuit. We wrote this as EMF equals to negative differentiate B with respect to T. So, from this Faraday's law, EMF, we also can write it as closed integral E dot dl. Closed integral E dot dl is the same as integral in bracket del cross E close bracket dot ds. So by using Stokes theorem, we can deduce it, and we can equals the integrals in bracket del cross E dot ds equals to 0. So the equation is equal, but ds cannot be 0. Therefore, del cross E is 0. Last but not least, Ampere's law as the fourth equations of Maxwell. The magnitude of the magnetic field is directly proportional to the strength of the current and inversely proportional to the distance of a point from a straight conductor. This is what the definition is supposed to be. And on the other hand, Ampere's second law also states that the line of integral of H is in a closed path is equal as the net current enclosed by a path. So we can write Ampere's law as a closed integral H dot dl equals to I, and I is also equals to closed path J dot ds. By using the same methods as the third equation, which is Stokes theorem, closed integral H dot dl is equals to closed integral in bracket del cross H dot ds, and we can equate into closed integral J dot ds. So in conclusion, del cross H is equals to J. Third Maxwell equation says that a changing magnetic field produces a changing of an electric, but there is no clue in fourth Maxwell's equation whether a changing electric field or magnetic field. To overcome this deficiency, Maxwell argued if a changing magnetic flux can produce an electric field, by then symmetry there must exist a relation in which a changing electric field must produce a magnetic flux. That's all from me.
Thank you to Dr. Ivy and our new guest. So I hope, and thank you also to our viewers. I hope you all gain something from this video, and please stay tuned for our next video. Thank you.
Don't forget to
Like and subscribe. Physics for Life.